Okay, so next week we'll have Lab 4, Monday and Tuesday groups. And so Lab 4 is going to be a experiment where we're going to work on some hologram multiplexing. Multiplexing is a really useful aspect of holography. And it's used for a variety of reasons. One of the main applications has been in holographic data storage. And we talked a little bit about that early on, where what you want to do is you have a, say you have a, like a spatial light modulator here, which has a lot of pixels that you can electronically define or assign, and then you have a beam propagating through that, say in a transmission spatial light modulator, and then that we may project that image onto a onto the hologram itself, holographic material here. And then, then we want to change that and maybe store another data set on the in the hologram. And so there's a variety of ways that you can multiplex. We'll talk a little bit about those shortly, but the main idea here, well, in our case, what we're going to do is simply to rotate the hologram and record it with a reference beam. And so there's you can do the multiplexing in a couple of different ways. One is to have a separate object beam and reference beam, and then we can change, say, the reference beam angle and do a second hologram with a different pattern in that object field, and so forth. So we can do what's, again, this would be called an angle multiplexing. And in addition, the way that the holograms are recorded is in a sequential manner, meaning that we, kind of do one hologram and then rotate, do another hologram, and we do it sequentially. It's also possible to do a simultaneous recording. So here, for instance, we may have several different signal beams or object beams coming in, and then we have a single reference beam, and we do the exposure just all at once. And this has, some benefits as well as some disadvantages as well. The benefit is that, as we'll actually derive this shortly, is that the efficiency that you can get with this kind of recording is significantly higher than what you get with this sequential recording by the way that you use up the available dynamic range of the material. Okay. The problem with this approach is that if you record this simultaneously, the way to optimize it would be to have the sum of all these beams here, the sum of the powers of all these beams equaling, say, the object beam, total object beam power, I equals 1 to, say, 5 there, and then set O equal to R for the power of those two beams, and do the recording, much like you've done in the past in the lab, for instance, where you have tried to balance the object and reference beam. And as we saw, if you do that, the visibility that you get for the fringes will be maximized. Okay. The problem, though, is that when you do a simultaneous recording like this, you then have each of these beams interfering as well, and so you end up getting other gratings, intermodulation gratings being formed with fringes that are maybe, again, oriented along the bisectors of those. All right, so you can get these intermodulation gratings which will detract somewhat from the overall fidelity of the reconstruction, because then when you reconstruct it with this beam, you'll in turn be reconstructing all of those beams at the same time, not only the desired signal beams, but also those intermodulation signals. However, again, you can get pretty high efficiency or higher DE than the sequentially exposed case. And this is a very useful kind of optical element if you want to do kind of optical signal broadcasting. You know, if you want to send a signal to, say, many receivers at the same time. So one of the applications that's been looked at in the past is for, say, an optical clock distribution in some type of optical computing system that you may be working on. So where you have to register all of your receivers with the same clocking cycle for the computational process. Okay, so all right. So the idea here, though, is that in both cases, and we looked at this to some degree before, there is a response of the material, say, to the exposure, which in turn is going to be proportional. If we're doing a phase grading, which we will be by and large, you're going to end up with a response characteristic which will translate into an efficiency characteristic that has kind of a linear range and a kind of a nonlinear range at very low exposures, and another saturation region up here at very high exposures. But at any rate, we have a limited range of, say, delta n that we can use in both cases. So the thing about multiplexing that you're kind of concerned with is how to use the dynamic range of the material so that you get kind of equalized efficiency. Most of the time you want equal diffraction efficiency for each of those gratings, right? If you were recording these kind of these bit maps for a data storage system, you would want a kind of equal brightness for each of those reconstructed images, because again, those would be projected onto a detector array, and so you want pretty good signal levels for each of those bit locations on the detector array. So if you were to, so let's say we're going to do, so for the lab we're going to do this sequential exposure here, and so how should we make the exposure? All right, so if we know that, you know, we have a range of exposure, you know, for our material, we said it was something like 18 millijoules per centimeter squared at 633 nanometers, and this is going to give us, say, a delta n about 0.03 for the bare material. All right, so what you might say is, okay, so we have 18, so we'll do 9 and 9. All right, so if you do that, however, many materials, silver halide was notorious for this, but photopolymers as well. If you did 9 and 9, the first grading that you would make may have an efficiency like this, and the second grading that you make will have an efficiency that will be somewhat lower than that. Okay, so here again, so this, if we did say 9 millijoules per centimeter squared and 9 millijoules per centimeter squared, we'll see that we have actually a non-uniformity in the resulting diffraction efficiencies. Okay, and the reason for that is that there is a kind of an enhancement to holograms that were to the holograms that were first exposed by the additional bias that's provided by the subsequent holograms that are given. And that kind of characteristic is sometimes referred to as a holographic reciprocity law failure. So if you have good reciprocity in your system, then you should be able to give 9 and 9 and get equal efficiency. But because of this kind of nonlinear curve that we have here, we don't always get that. All right, and so so why does that occur again? So if we look at the material, say this bare material that we have, so we give it the first exposure. Again, we have these regions with say very high efficient or high illumination here, and we have a monomer that's polymerized in those regions. Like so. And then we would start to get a kind of a diffusion process occurring. If you then give this a second exposure, all right, then there's an additional enhancement, right? Because we're still getting some, these are the high levels, high exposure areas. If there's another high exposure area here, there's usually some average exposure as well. It's not completely zero. So you're still illuminating these areas and polymerizing some additional monomer in those areas. And that would be lacking in the second hologram that was made. Okay, and so that gives rise to kind of these non-equal diffraction efficiencies that you would get in a resulting hologram. All right. Okay, so anyway, so that's one thing that occurs in the multiplexing. So what I'm going to have you do in the lab is to first do an equal exposure sequential hologram, multiplexed hologram, and then the next one, what we'll do is we'll actually reduce the exposure of the first hologram by, I don't know, I think I mentioned 25%, which is pretty high. But that way, you can see if there's some compensation for that unequal exposure. What may happen is that the second one is higher. Initially, the second one might be lower, and then in the second case, the second one might be higher. But that means that you kind of found the sweet spot. It's somewhere in between those two exposure, or 0 and 25% for the compensation will give you the optimum reduction in that non-uniformity in the diffraction efficiency. Okay. All right. So for the multiplexing experiment, what we'll do is we'll use the bare material. So we have the thickness again is about 16 microns for the bare material, and so what I'd like you to do is to expose this with two beams that are, so we'll have them at say 20 degrees and 40 degrees, and then rotate the hologram by say 40 degrees here, so that we're now going to illuminate it with minus 20 and minus 40. What?
That's a 60-degree rotation.
Let's see. So we will rotate. We have it here, and then we're going to rotate it. I guess, yeah, not 60. It would be.
You're going from the 20 to the minus 40, right?
Yeah, yeah. So if we want to so we're going to have it here, minus 20 and then minus 40, so it would be so we want this then to come in at 60, you're saying?
That's a 60-degree rotation. If you were doing it just 40, you'd be adding minus 20 and then incident.
I think he's just saying relative to the x-axis.
Okay.
Yeah, so here, I mean, here's 20, right? So if we rotate this this way by 20 and come in with these here, so then, I don't know, I don't think very well on the fly too much sometimes. If we, all right, so here's 20, and then we're going to say the same beams, right? So here, if we then, yeah, I guess you're right. You'd have to rotate it 60 degrees in order to get on the opposite side. Sorry. Okay. So at any rate, that'll give you, again, so your inner beam angles or your bisectors are going to be along these two directions for the two gratings that are set up. And there's, in addition to this delta n that you're using, for the holograms that you're going to make, there's going to be a diffraction efficiency curve, all right? So you may get something that looks like that, say for, if you're reconstructing this hologram, you'll get an efficiency curve that looks like that. You're reconstructing that one, you'll get an efficiency curve that looks like that. So what happens here is that you're getting kind of interference between, or intermodulation, I should say, not interference so much, but a kind of an intermodulation effect for those reconstruction efficiency plots. So if you were, for instance, in a data storage system like this, that intermodulation that you have is going to cause an error in your detection process. And so your kind of your bit error rate or your error rate that you're going to end up with for the storage system is going to be higher in that system. Okay, so one thing I want you to explore a little bit is to see how far apart these efficiency curves are. Are you going to have the overlap, or can you make two holograms that don't overlap in this material? All right, and again, the way you can get at that is by looking at that detuning parameter that we talked about, which for the small angle, say delta theta deviations from Bragg, those were equal to, say, k times delta theta sine of phi minus theta 0 minus delta lambda over 2n lambda. Now in this case, since we're not changing the wavelength, that term is 0. And we saw that the efficiency curves will drop for the detuning when that value was around 2.7 for transmission hologram. This was that eta over eta 0. And this was for the maximum, say, efficiency. And that eta, or I'm sorry, chi, was equal to the detuning parameter d over 2cs. So when this is equal to 2.7, you can actually calculate, say, what that detuning angle will be that you can get away with on separating the two holograms that you're recording, right? So I asked you here a couple of questions on that. So for instance, initially I just asked you to calculate for your specific case here what the selectivity of that hologram is, and so you would use this approach in order to calculate that, all right? And then I ask you a more, not a problem related to, well, it's related to the lab, but using a different material. So what if we have a data storage material that might be, say, 200 microns thick, and also recording with a wavelength here of 0.6328 microns, and assume that you have the kind of the maximum efficiency value. So that would correspond to a nu here, which is pi over 2. Remember, we could just assume, say, sine squared of nu is equal to our efficiency, say, for an unslanted grading. So with this, you can get an idea of what the bandwidth or what the selectivity of those holograms are, and see how many you can pack into a recording where you're, again, rotating that material to do subsequent recordings of each of those sequential holograms, okay? So it's a little bit, it's a different material than you're actually working with, but one which is quite useful because it will allow you to get an idea of how many holograms you can actually record, say, in a polymer material that's of some thickness like that. There's other multiplexing methods. You can do wavelength changes, which is a little more difficult. But another change that people have found to work is, instead of just doing a rotation of the material, you actually do a rotation about the optical axis. It's called peristrophic rotation. So in addition to this rotation, you can think of the material as rotating kind of around the optical axis in that way. So that's another way that you can kind of pack in some more data into the medium. All right. So there is this efficiency that we have. Again, this is related to the delta n, the index modulation, where again the nu sub I that we have, say, for each hologram. So if we had multiple holograms here, nu sub I is equal to pi delta nid over lambda, say, cos theta. And so the efficiency this is equal to the square of the sine. But for small, say, delta n's, right, we can kind of say that the square root of the efficiency is about equal to, or is proportional at least to nu sub I. And this is, I would say, proportional to our delta ni, all right? So there is a measure that's often used for multiplexing called the M number for a hologram. And what that M number represents is kind of the number of equal efficiency holograms that can be recorded in a medium that has a certain delta n. So what you can do is you can take your material, figure out what make a single great exposure hologram, find the maximum efficiency, and then calculate using, say, this relationship here, the delta n that would correspond to. And then you can construct what's called this M number. And the M number is just equal to, again, we have the square root of the number of holograms with a certain efficiency, and we have M of them. So an M number of, say, 2 or 3 or something like that is actually pretty good. For the data storage problem, you may not need very high efficiency to get good signal detection if you have a sensitive camera. And so a lot of times the efficiency that you would have might only be a tenth of a percent even. So if that were the case, then the number of holograms that you have can be pretty significant, on the order of 1,000 or so. Okay, so again, there's a lot of trade-offs there, and we'll come back and look at that a little bit more later. But this M number is a pretty good measure of hologram performance, and it really is simply a reflection of the material characteristic for that holographic recording material in terms of what is the delta N, what is the material response range that you have for that material. Okay, so any questions on the lab? All right. I thought I'd take a little diversion today, just briefly, and it relates to, again, some hologram material characteristics. And so a number of, so I think in the last lab, actually, I asked you to calculate what sort of effect you might have if the hologram shrinks or swells, or you have that change in the Bragg angle. Well, there's kind of an interesting effect that we found very recently, because we were trying to make holograms for a solar application. And so here you have broadband solar illumination coming in. So you have a large delta lambda coming in. And of course, this would be a transmission hologram. And it's recorded so that one beam is at normal incidence and one beam was at some angle, about 20 degrees to that normal. So the fringes are actually slanted a little bit. But the interesting thing is, for this, what we were trying to do is create a dispersion pattern. The different wavelengths, of course, are going to be separated. And those, that, again, match the K-vector closure or Bragg condition with pretty closely, are going to give us the high efficiency. And those are going to be at different wavelengths, right? So, and they have to be separated at different angles in order to do the Bragg matching condition. But the question that we had, we're trying to figure out, so our material, we find that it swells during the processing. So we're using dichromate gelatin, and so if we have a material that looks like this, if it swells, then these fringes are going to rotate a little bit, right? So they're going to kind of spread out a little bit, and so that this angle is going to decrease slightly. So what does that mean in terms of the K-vector? So again, here is X and here is Z. So our K-vector, again, is, the original K-vector is normal to these fringes, and then the subsequent K-vector is normal to these swollen fringed fringes corresponding to the hologram after the processing. All right. So so one of my students, Shelby Vordran, she asked me. She said, "Okay, so what does this? Should this shorten the wavelength, or decrease the wavelength, or increase the wavelength?" So my first inclination was that if you swell, you're going to increase the wavelength that does the Bragg matching for this. Okay. Now that's always true for reflection holograms. However, for a transmission hologram, it can either decrease or increase depending upon which direction you reconstruct it at. Okay, so that was something that was a little surprising to me. I didn't think it would change for that. But let's look at that. I think this is very instructive from perspective of looking at this from a Bragg circle diagram. So here is the Bragg circle. And so we have one beam which is normal to the surface. And again, so this is our x-axis and z-axis. So we want to reconstruct it so that the hologram is pointing towards the sun and then diffract the light off at some angle, all right? So we have this angle, and then we have another angle, say at about 20 degrees, all right? And so the k vector that we have is maybe in a direction like that, okay? All right, so now, let me make it a little bit more slanted. All right, so what does it mean when this grating swells? Well, here we have here's our volumetric period for that grating. And it's also, it's a spatial value. And it has and we can think of this as having an x and a z component. So here we have a lambda z. Here we have a lambda x for that component. The lambda x, by the way, is not equal to that value. This value is, here is the projection of this period onto the surface, okay? Remember when we derived the imaging relations, we had k dot t, right? And so this k dot t is equal to k cosine of phi, which is the angle of k relative to t. And so this is 2 pi over lambda, or times cosine of phi, which is 2 pi over lambda over cosine phi, which is the projected value for that. Okay, so it's a little subtlety that also comes out of this. But at any rate, we can say that we have a k vector which is equal to 2 pi over the period component in the x direction plus 2 pi over the period component in the z direction, right? All right, so what happens when this swells, all right, is that lambda z gets bigger, okay? And when lambda z gets bigger, k gets smaller. Kz gets smaller, all right? So if we look at this Bragg circle, what does that mean? That means that this k vector, I didn't draw it very good here, or very instructively, but this k vector is going to have a slightly less k prime. Let me draw it a little bit differently.
Use that as the new one.
Here, I'll just draw it here. Okay, so here is k. So this is an expanded view of that trashy drawing I just did there. So we have k like that, and then k is going to rotate to some new value. It still has a component, so this is k prime. It's going to rotate like that, right? And there's no change in the x. We're assuming no change in the x. So there is a delta kz, which is going to go that way, right? Because that means that we're decreasing the z component, okay? This is our z-axis. So there's less of a z component. So what happens when that occurs on this Bragg circle? Well, now, again, so this, we have a bisector we can draw like that for the original one, okay, and then we have another bisector here which is going to kind of come off like that, right, because it kind of rotated like this one is showing here, okay. So when that rotates, we want to reconstruct it at the same direction here, all right, along the z-axis. So to get the k vector closure, right, so if we have that, we need a longer K2, 1. All right, so here's K2, 1, here's K1, 1. So we're going to need a longer propagation vector in order to intersect with that bisector, right? And then the other part of this is like this. Right? So this is also same magnitude as that, but a different direction, K2, 2. Right? And here's K2 or K1, 2. So what does that mean? That means, right, so this is equal to 2 pi n over lambda 2. So lambda 2's got to be shorter. Okay? All right, so that was Shelby's view, and I said, how could that be if you're swelling? Well, now let's do another one. Same kind of idea. All right, so we have construction at one angle or at one wavelength here. So we have that direction along the z-axis, and we have our other direction at, say, 20 degrees, like so. And here's our k vector, all right? So now, if the k vector, so here's k, the k vector rotates towards the z-axis, all right? Again, here's the bisector for this one, and now here's the bisector for the second grating. All right? So if we're this is the reconstruction direction there, and this is the reconstruction direction for this case. All right? So if we're now reconstructing this way, then this is the new intersection, right? And that is a shorter length than that original one, which means that the lambda now, lambda 2, is greater than lambda 1, okay? And so sure enough, we went into the lab and looked at it, and when you reconstruct with one direction, you get a shorter wavelength. When you reconstruct with the other angle, you get a longer wavelength, okay? So what seems to be happening is that your dispersion relationship, when you do a swelling, the efficiency curves kind of move in a, if you think of the angle would move sort of towards each other or away from each other, depending upon whether you're shrinking or swelling of that material. So the same kind of phenomena is occurring with the wavelength. And it shows up usually, again, so you can do the Bragg matching we're illuminating with all wavelengths. So one of those wavelengths matches, and it turns out that they are opposite depending upon whether you're looking at one of the reconstruction directions versus the other. So I thought that was kind of interesting. I never really appreciated that before we tried doing that, because I never really forced the direction of reconstruction to be only one direction. But kind of, counterintuitive. I think it's counterintuitive that you can get either a longer or shorter wavelength with the same change in the material. Especially in this case where swelling it would, in my way of thinking in the past, was that you would always get a longer wavelength that would give you the optimum reconstruction. That's true again for reflection gratings because you have compression of those periods, and so it's like a interference filter, like a thin film interference filter, where you get your lambda over 2 matching for the for the index difference characteristic for that thin film material, to kind of give you the nulling for, say, an anti-reflection coating. It's sort of the same idea, except now we're getting enhancement instead of reduction of that reflection coefficient. Anyway, I'll put this up. I made a little write-up for this, so you can have a look at that and use it in your future if you so desire. Okay. All right. So what I'd like to do now is to kind of finish up what we were talking about for the efficiency characteristics for a couple of different grading types. So we finished the transmission grading, and now we wanted to look at the reflection grading situation. And so our general solution that we had is along the cases of, for reflection grading, if we wanted to look at a specific case of, say, a phase grading, we have that again, for phase grading, we have the kappa, the coupling coefficient is pi and 1 over lambda, and the absorption, the average absorption and the absorption modulation are both equal to 0. All right, and so if we plug those values into our general equation for the reflection hologram, we end up with an amplitude function S, which is equal to C sub r over C sub s, being the cosines of our reconstruction and diffraction beam, to the 1/2, all of that, or that divided by j times psi over nu plus 1 plus psi squared over nu squared to the 1/2 times the hyperbolic cotangent of nu squared minus psi squared to the 1/2. Okay, so all of this is in the denominator. And we have, we can utilize here a new value that we would have is that this is equal to j pi n1 d. Now we use this j being in this term because C sub s is negative. Okay, so this is less than 0. All right, and so we end up with a kind of a j factor out there. So we have to account for that. So we'll use it here. And we have lambda CR CS to the 1/2. So here, this gives us a j and that gives us a j, so it cancels out. And then we have for the psi, that's equal again to the detuning factor d thickness over 2cs, which again, this is negative, so that will cancel that out. All right. So when we go ahead and calculate the efficiency for this, so we have eta now is equal to C sub s magnitude over C sub r s star. What we have then is the following. All right, so we end up with eta is equal to 1 over 1 plus 1 minus psi squared over nu squared divided by the hyperbolic sinh squared of nu squared minus psi squared to the 1/2. And now if we multiply sinh squared times top and bottom, we end up with the hyperbolic sinh squared nu squared minus psi squared to the 1/2 over sinh squared of nu squared minus psi squared to the 1/2 plus 1 minus psi squared over nu squared. Okay. Now, notice that the cosh squared is equal to 1 plus sinh squared. All right, and so that's handy because if in fact, so here we have that here, right? So we can substitute that with the cosh of, or cosh squared of nu squared plus psi squared to the 1/2 minus this factor. And this factor depends on the detuning parameter, right? That psi squared. So if the detuning is 0, all right, so if psi is equal to 0, meaning that this detuning parameter is equal to 0, or we are at the Bragg condition, then we end up with the following. We have that eta is equal to the hyperbolic tan squared of nu. Okay? So that's quite useful. Okay? And so that means that we're going to have a curve that's very different from the transmission case, which was that oscillating sine squared function. Here, we're going to have a curve for the efficiency which will saturate, okay? And that kind of makes sense, right? I mean, if you have a reflection hologram and you come in here with a certain beam, you diffract more and more of the light out. There's going to be a limit to how thick you can make this and still have any light left that is going to be able to contribute to that diffracted field, right? So there's not that, it's not like in the transmission case where, here we have the light comes in and then it produces a diffracted field. That diffracted field then rediffracts and gives you more reference field, so you can get that kind of sinusoidal case where we have, again, the eta for the transmission case is sine squared of eta. In that case, you get this interplay as the beam moves through it, going back and forth. Here, you're just depleting that incident beam, and eventually there's no additional thickness. That's just going to increase the overall efficiency of that grating. It'll get very close to 1, as you can see here. But it doesn't oscillate in that same manner. Okay. All right. So what if we have now some absorption in this? Or what if again? So what if we're not at the Bragg condition and we have kind of this general form here? Here we can have a plot similar to the one that we did for the transmission case, where we found that at psi here, this detuning, so this is the off-Bragg. So again, this incorporates the detuning parameter. So in this case, for the reflection grating, the efficiency is going to decrease again and start to increase. But here, the detuning is broader, so this goes out to a value of about 4. This is your efficiency starting at 1, whereas in the transmission case, that value was equal to about 2.7. All right, and so if we look at that value for psi, again, that's equal to delta theta pi d times the sine of theta 0 minus the phi angle, okay? And in this case, for reflection grating, for unslanted reflection grating, phi is 0. For an unslanted reflection hologram. It could be off from that too. I mean, it doesn't have to be 0. But for an unslanted transmission grating, the phi is equal to 90 degrees, okay, for that case. So those orientations are different. And so we have this divided by the period times c sub s. And we have here that this is delta lambda pi d over 2 times the period squared c sub s. So this is the psi, includes the tuning parameter, also the thickness. So if we wanted to make the hologram more selective, all right, we can do a couple of things. One thing we could do is, of course, make the hologram thicker, again, up to a certain point, right? If we made this bigger, then increasing delta theta by a smaller amount will have the same overall value of psi. And we see that it dips to 0 here at a value of 4. It doesn't matter how we get it. We could increase d or we could increase delta theta. But we can control that by, again, making this as thick as we can and still get, kind of an optimum efficiency. Or we can also decrease the period, right? And we can do that both for the angle and for the wavelength in order to make higher selectivity gratings. Okay, so what about if we have some loss again? So that was another case that we had looked at. So if we have, again, this the lossy reflection grating or reflection hologram. So here the the relationships for the reflection holograms are a little more complex than in the transmission case. But at any rate, we can always, what I usually do is just write a small computer program to use the general form, which is this c sub s over c sub r times the coupling coefficient over alpha 0 plus j times our detuning parameter plus c sub s times gamma 1 e to the gamma 2d minus gamma 2 e to the gamma 1d over e to the gamma 2d minus e to the gamma 1d. And all of that squared. All right, because the relationships have all these hyperbolic cotangents and all this stuff. So I find it easier, and then you can just add whatever you need to the gammas. If you have absorption or an absorption modulation, you can always add that to the result. But let's just look at a couple of effects that I think are interesting for the lossy reflection grating. So here is a couple of curves that I generated just using this expression that we have here and incorporating some average loss. All right. So, and this is for an unslanted grating, reflection grating. And so here, here's without any loss. And so this is kind of the detuning, but specific to the angle detuning from the Bragg condition. So here we're going, this is for a 10 micron thick with an index modulation of 0.05. And so we get a really broad, about almost 20 degrees here. Well, about 16 degrees before you see almost no variation. But then if you go a little further, it starts to fall off. And this will start to roll off if you go really far off. And the effect of absorption at an average absorption is kind of like you would expect. It just mainly decreases your overall efficiency. Okay. Now that's for an unslanted case. If we look at the slanted hologram, so again, using this same relationship here, whoops. But we now have a slanted hologram. The construction angles are 0 degrees and 150, so 30 degrees off the z-axis in the negative direction. And we notice that when you slant it, you create a kind of an asymmetry here, right? You notice here we have so for this is the zero loss case. So this comes down, nice null here, and then it peaks up rather quickly, and then drops again. Whereas on the other side, on the negative side here, it's rising or it's changing more slowly. Okay, so the grading, when you make this slanted grading, it introduces some asymmetry into the diffraction efficiency characteristic. Now, if you add some loss, you know, as you might expect, you get a drop in the peak efficiency. The curve looks reasonably much the same, but another important result of that is that these nulls don't go all the way to 0. And so whenever you see that in a diffraction efficiency curve, that will tell you that there's a little bit of residual loss in that hologram. Okay, and so you'll get this upwelling of those nulls. They won't quite go to 0, and that usually is indicative of some kind of loss, average loss that's in the hologram. Okay, let me just go through one more type of reflection grading, and that is if we have just an absorption reflection hologram. Okay, and so for the absorption hologram, we have n1 is equal to 0 this time, and we have a kappa which is equal to minus j times alpha 1 over 2, and also we're going to have some average absorption which is not equal to 0 as well. All right, so the efficiency for this, we can write that out. Okay, it's not too messy, and that's equal to 1 over psi over nu plus psi over nu squared minus 1 to the 1/2. That times a hyperbolic cotangent of nu times psi squared over nu squared minus 1 to the 1/2, and all of that is squared. Let's see. Yeah, okay, so all of that is squared. That's what I wanted. Okay, and here nu is equal to alpha 1, the modulation, absorption modulation, alpha 1 d over 2 cos theta 0, and the psi is equal to alpha 0 d, again, that's the average absorption that we have, over cosine theta 0, and minus j times, finally get to use chi 0, and chi 0 is related to the tuning parameter. So we have delta theta beta d sine of theta 0 plus delta lambda k d over 2 lambda. Okay? So let's look at this. So before we calculated an efficiency for the absorption transmission hologram, we had an efficiency which was equal to 3.7%, and for the thin absorption hologram or grading, we had an efficiency for the plus and minus 1 orders was 6.25%, if you recall. So let's see what it is for the reflection case. All right, so we'll be at the Bragg condition. So what that tells us is this chi 0 is equal to 0. And we'll take alpha 1 is a maximum. And so that means that alpha 1 needs to be equal to alpha 0, right? The average absorption, that's the maximum modulation we can get. And when that's the case, then we have two inputs here. This part is going to be 0 because we're at Bragg, but this part's not. So when we have this condition, this is going to tell us that chi over nu, if we do that ratio, that's going to be equal to 2. Okay? And so now if we look at this relationship, make this substitution, we find that we have eta is equal to 1 over 2 plus the square root of 3 hyperbolic cotangent of nu times the square root of 3 and that squared, okay? And for the hyperbolic cotangent, as nu gets larger, all right, this whole value goes to 1. And so this, for kind of the maximum case, we're going to have this is equal to 1 over 2 plus the square root of 3 squared, and that's equal to 0.0718, or we have 7.18% for the reflection hologram. Okay? So we get a higher efficiency for the reflection hologram. And again, we can think of the reason for that as the following, is that, you know, in the reflection hologram, the beam is being depleted and it's passing through that medium in the back direction, whereas in the transmission grating, the diffracted beam has to pass through the entire thickness of that grating. Okay, so there is kind of a bit of an advantage here in having a reflection absorption grating in terms of efficiency. Not much, but it's kind of interesting that you do get higher efficiency than the transmission case. Okay, so what I'd like to discuss a couple of other issues. So that kind of completes these different types of holograms that we might get for the approximate coupled wave model. And so, you know, for the approximate coupled wave model or the Kogelnik model, you know, we made several assumptions. They were made. So how do we know when they're satisfied? Okay. So Kogelnik actually, you know, again, pretty great paper. He addressed this issue and came up with what he called a Q parameter. And so since then it's been called the Kogelnik Q parameter for volume holograms. And this parameter is equal to 2 pi times lambda in the medium over the period times d, the thickness of the grating, also over the period. All right, and what he said was that if this parameter, if this Q parameter is about greater than or equal to 10, then you'll have a thick or volume hologram, and you can use his approximate coupled wave model. Okay, and that's pretty important to know, because if you don't, you know, kind of check that, what will happen is you'll start to predict much higher efficiencies for situations that are more of a thin hologram than you should be able to get. Okay, so for instance, again, if you have a holograms has some thickness d here, and you're illuminating it with one angle, and then let's say if you try to, so here's the 0 order, and you have a diffraction angle that's, you know, very close to that 0 order. All right, what's happening then is your fringe planes are going to be very far apart, which means that, again, so the wavelength to period ratio in that case is going to be very small, okay? Because the period is going to be, say, very, very much larger than the wavelength. Now, again, you can also think that if you had, for thin grating, here, what that means is that the material is thin compared to that period. And so that's where this factor comes into play. It shows you how many periods you can fit into the thickness of that material. Here you see what the relationship is between the wavelength and the period. Okay, so for a lot of volume holograms, the grating period is on the same order or even smaller than the wavelength. Okay, so you need to always check that Q parameter. Now, there was this other paper that Moharm and Gaylord wrote. Well, they actually wrote a separate paper on this. There was this review paper I was referring, or that proceedings paper, but they actually addressed this in a totally separate journal paper. But they had found, they were looking at photorefractive crystals, and those crystals are centimeters thick. Okay, so you would think that this condition would automatically be satisfied if you were operating in that in this regime with a D, which is on the order of 1 centimeter, and the wavelength, they were probably using 514, an argon laser line, and so you would satisfy that Q being greater than 10, but they found that they were actually getting some multiple orders that were being generated, which were very significant. And so they came up with another criteria for the region in which the grating is operated. So it's criteria for thin and thick holograms, okay? So what they said is, all right, so if we have a thin hologram, as we found, then the efficiency, eta sub I, is a Bessel function squared, right? That first order Bessel function that we had. And same argument, though. We have 2 pi delta n d over lambda cos theta for the argument of that Bessel function. And if we have a thick hologram, we now have this nice simple relation that eta is just equal to sine squared of pi delta n d over lambda cos theta. So we're off by a factor of 2, but we have kind of the same argument for both of those. All right? So what they said is, okay, so let's set up a criteria whereby if we have the actual efficiency, eta sub I, minus this j sub I squared of, we'll just call it nu, or times 2 here, when that is less than some epsilon, then we'll be in the thin hologram region. And similarly, when we have the efficiency for this thick grating, the actual efficiency, minus sine squared of nu being less than or equal to epsilon, then we'll be in the volume region. So again, so when the power associated with the efficiencies are less than some value, then we're going to be in one region or the other, okay? So what they found was that for the thin grating, if we have the product of 2 pi lambda d over n0 cosine theta lambda squared, so that's somewhat similar to what we had here for the Kogelnik case, right? We have lambda over period and d over period, but then times the modulation that they had. So we have pi delta n d over lambda cos theta, when this product is less than or equal to 1, then we'll be in the thin region, okay? And so they gave this a value of q prime, because it's very similar to Kogelnick's parameter, except for this 2 pi over n0 value. And this value is, they called it gamma. And so when that's less than or equal to 1, you'll be in the thin hologram region. Now, for the, I guess we have a little line there. For the thick hologram case, here they said if we take these same parameters, this and that, and take a value of q prime over 2 gamma, all right, when that value is greater than or equal to 10, then we'll be in the volume region, all right? And so they went ahead and they made some plots of this to show these different values. So they made a plot of the this modulation parameter, gamma versus q prime. And so they come up with, it's a logarithmic plot. So here's 1 and 10, and here's 100 and 0.1. Okay, and so what they found was that they plot this product here, which is 1, and they get a curve that comes down like that. So this is for q prime gamma equals 1. And then they do this value where q over 2 gamma is equal to 10. And they got another plot that looked like this. Okay, so this is corresponding to that. So everything they found consistent was that everything out here was definitely in the thick hologram region. Everything to the left of this line was in the thin hologram region. And here it was kind of a mixture, meaning you can get multiple orders being diffracted in this kind of intermediate region. So that was the area that they were operating in with this photorefractive crystal that was, a centimeter thick with a visible wavelength, which should have been in the volume region, but it wasn't, because it was still not satisfying this additional criteria that they found to be important. Okay. So anyway, so when you're making holograms, all right, and want to know if you can use the approximate coupled wave analysis, you need to do a little bit of checking of the criteria and make sure the assumptions are satisfied. Okay, so we'll see you next Tuesday. Thiago's here. Did you have homeworks to pass out? Okay, he has some homeworks for you, and I have some assignments for him. So, yeah.